Hello, good evening, what's up, and welcome to another video of our 1001 MSc online tutorial series. My name is Brock Grant, and today we're going to be covering chemical bonds and molecular geometry. So, in this tutorial, we're going to be learning a couple of different things and a lot of very important topics that will span across the rest of this semester and especially in second semester. So we're going to be covering different types of chemical bonds, so different ways that these elements and atoms hold themselves together. We're going to be looking at Lewis structures, electronegativity, polarity, and VSEPR, or valence shell electron pair repulsion theory. Prerequisites for this module, I highly recommend that you check out Module 3, the atomic theory video, so both Part 1 and Part 2. As the knowledge of how these protons, neutrons, and electrons all work together within an atom and their properties relating to the periodic table will be exceptionally useful in this module. Okay, so let's jump right on into it. So let's look at Lewis structures. So Lewis structure is essentially a visual representation of an element showing its valence electrons. So most notably during the atomic theory videos, I often referred to the valence electrons by drawing it thusly. I would sort of draw the nucleus, like thus, and I would sort of draw these different levels, energy levels around that nucleus, and I would sort of refer to these electrons on the outer part here as being the valence electrons. And this is correct. That does represent valence electrons. However, as you can imagine during your exam, when you have to answer a lot of tutorial questions, this method that we see here becomes very tedious. Okay, it takes a long time to draw out, it's very space consuming, it's very easy to make a mistake. So what we do is, instead, we can write it in a different way. So let's look at boron, for example. So boron is the symbol B on your periodic table, and it has the electron configuration 1s2, 2s2, 2p1. So as we remember, valence electrons are electrons in the outermost shell, which is your s and p orbitals. So we can see, judging by this electron configuration, that it has 3 valence. However, another way that we can represent it is like this. So what we do is we write down the element formula. So in this case, because we have boron, we write B. And we fill in the electrons, the valence electrons, until we reach 8. So let's look at another example. Let's look at, say, oxygen. So if you look on the periodic table, and again, you count across, you would see oxygen would have 6 valence electrons. So what we can do is, we know that oxygen has 6 valence electrons. So I draw the elemental symbol for oxygen, which is just O. And what we do is we can go like 1, 2, 3, 4, 5, 6 electrons. And that is how Lewis structures work, in that we can just use a visual diagram like thus to see how many valence electrons an element has, and this becomes very useful in determining a compound's 3D structure, which we'll see at the end of this video. So, what does boron have to do with its valence electrons to become stable? So what we do is we can look at the Lewis structure for boron, and we can see it has 3 out of the potential 8 electrons. So as we remember too from our video in atomic theory, that all elements strive to have 8 electrons in their outermost shell. So we can look at boron here, and it has 3. So this is when we ask ourselves, what is easier? Is it easier for boron to steal 5 electrons, so to find other elements around it nearby and try and steal 5 electrons? Or would it be easier for it to try and get rid of 3? The answer is to get rid of 3. It is a lot easier just in terms of the sheer number to get rid of 3 than to try and steal 5. So for boron to become stable, it needs to find another element or compound or something else to steal or take away these 3 electrons. Because by doing that, it will drop down to the lower energy level, where its outermost shell would have 8 valence electrons. So let's look at how we can draw valence electrons. So the first thing that we need to do, which I have said in the previous slide, is that we must follow the octet rule. And that is that all elements strive to have 8 electrons in their outermost shell. In order to draw these Lewis structures, the first step that we need to do is we need to identify the central atom. So in most cases, this will be the least electronegative element. So let's look at CH2O. So we look now at our central atom. So our central atom would be carbon. So if we draw carbon, now we have a look at carbon on the periodic table, and we see how many valence electrons carbon has. Now remember, you will have a periodic table in every single examination you do. There is no need to memorize what elements have how many valence electrons. So if you look on your periodic table, you would be able to see that carbon has 4 valence electrons. Now carbon is not happy. We can see that at the moment because we can see that carbon has 4, it wants 8. So we have a look at what else carbon is bound to, and we can see it's also bound to hydrogens. So this is where we can draw our hydrogens in. So I'm going to put 1 here and 1 here. Now, instead of putting a dot for a valence electrons for hydrogen, I'm going to draw an X. The reason why is just so you can differentiate between them. So hydrogens have 1 electron in their outermost shell. So I'm going to put 1 and 1. Now, this is where we can see that these are covalently bonded. Now, I'm going to talk about covalent bonding in a moment. But however, we're not done yet, because we can also see that carbon is bound to oxygen. So what we do is we draw our oxygen. Now I'm going to draw an oxygen as little squares. So if you, again, look on the periodic table, you will see that oxygen has 6 valence electrons. So that's everything included now. So what we need to do is we need to go through each of these elements here, and we need to check and see if each and every single one of them are happy. So by happy, it means is the octet rule being abided? So let's look first at our hydrogen over here. Is hydrogen happy? So we can see that hydrogen has 1 electron here and 1 electron here. So for hydrogen, its outermost shell is the s orbital. So hydrogen is one of the exceptions where it doesn't need 8, it only needs 2. Because remember, it's the outermost shell. So hydrogen is happy, so that's good. We can give that a bit of a tick and move on. Looking now at this hydrogen. So again, it has 1 electron here and 1 electron here. So that means that hydrogen has 2 electrons in its outermost shell. So hydrogen happy. Now let's look at carbon. So carbon has 1, 2, 3, 4. But because it's bound to these elements, it also has their electrons too, because they're being shared. So 1, 2, 3, 4, 5, 6, 7. Okay, so carbon is not happy because carbon only has 7 electrons in its outermost shell, not 8. So looking at oxygen, 1, 2, 3, 4, 5, 6, 7. Okay, so oxygen isn't happy either. So what this tells me is that both carbon and oxygen are an electron short. So what we can do is, if we look here, we can see that we have an electron over here, just chilling, not doing anything. And we also have a spare electron over here, just chilling and doing nothing. So what they will do is, these electrons will want to go to each other, and they'll want to form another bond, because then carbon and oxygen will be able to share that extra pair. So this is called a double bond, because we can see that carbon and oxygen will be bound twice. So if I redraw this, okay, so this is what our compound would look like. So please forgive me for my horrible handwriting. So let us have a look now. So hydrogen needs 2 electrons to fulfill its outermost shell. So hydrogen 1, 2, hydrogen 1, 2. So these are happy. Now let us look at carbon. So carbon has 1, 2, 3, 4, 5, 6, 7, 8. Because remember, these are forming a bond because the electrons are passing back and forth. So carbon now has 8 electrons. So we can give carbon a big tick. Happy days. Now let us look at oxygen over here. Oxygen has 1, 2, 3, 4, 5, 6, 7, 8. Oxygen is now happy. So what that means is that our overall structure of CH2O is going to be hydrogen, carbon, hydrogen, double bond, oxygen, otherwise known as formaldehyde. And that is how you can use Lewis structures to determine how compounds are bound in real life. Now that we've finished looking at Lewis structures, we're now going to have a look now in the introduction of chemical bonds. So the first one is the ionic bond, and this occurs via the transfer of electrons. So the example here is sodium chloride. Now I'm going to go through examples of each of these in a moment. The next type is covalent bonding. So covalent bonding isn't as rigid as ionic bonding in terms of one donates and one steals. A good way to think of covalent bonding is that the 2 elements will share an electron, and they'll sort of pass it back and forth between each other. Now, this third one, the metallic bonding, you do not need to know. Okay, for your exams, you will not be examined on what a metallic bond is, being able to identify it, none of that. You will, however, definitely need to know an ionic and covalent bond. Now, again, remembering that when we were looking at our Lewis structures, we were able to use our Lewis structures to determine what a chemical looks like and how they bind together. And this also links to when we were looking at nomenclature of inorganic compounds, when we were looking at the charges of these compounds. Again, these all tie in together because the whole purpose of a bond is so that atoms that have an incomplete number of valence electrons can fill out that outer shell. So they can have 8. This is why we find noble gases, which is the gases on the far right of the periodic table, to be very unreactive because they've already got their 8. So if I was to write neon would look like this. So it wouldn't want to bind to anything. It doesn't have to. It can just sit there by itself and go, no, you know what, I'm fine. I don't have to bother about trying to donate electrons, to try and steal electrons. There's just no need. And that is why they just simply do not react. So something I want you guys to keep in your minds is that all chemical bonding, whether it's ionic, whether it's covalent, even metallic, it all comes down to electrons. The stability of an element all boils down to electrons. So, as we now look in electrons, this is where we can see atomic radii. So atomic radius is how big the atom is, how far away the outermost electrons are from the innermost nucleus. Now, here's the trick though. As you move further and further away from the nucleus, so as the atomic radius is getting bigger, or the atom is getting bigger, the distance between the outermost shell and the nucleus is getting greater and greater. Now picture for me if you hold two magnets together. Now if you hold those magnets very, very closely, the attraction is quite powerful. Okay, they will really want to try and sort of snap to each other. But as you move those magnets further and further apart, we notice that they still attract, they still want to pull towards each other. But the further we pull them away, the weaker that attraction gets. And the same thing is when we look at atomic radius and being able to sort of steal these electrons. Now I'm going to cover that more when we talk about electronegativity and polarity. However, what I want you to memorize, the big takeaway part of this, is that as the atomic radius gets bigger, the strength of the attraction will go down. So let's look at these bonds a little bit more closely. So let's look at the ionic bond. So the ionic bond, as I said before, is the exchange of electrons between elements. So as we look at sodium chloride, which is a nice simple example, we look at chloride. So on the periodic table, it has 7 valence electrons. And we have sodium. Now sodium is on the far left-hand side of the periodic table, and we can see it has 1. Sodium is not happy with its current arrangement. It's overshot. It's got 1 extra, it needs to get rid of it. You've got chloride here. It's being particularly moody. It's being swingy because it needs just 1 more electron and then it's happy. It's stable. So it needs to try and find that 1 electron somewhere. So what it does is it will sort of steal this sodium, and this is where we have this ionic bond. So we'll have sodium and chloride. 4, 5, 6, 7. Now we can see that chloride still has its 7 electrons and sodium still has its 1 electron, but because the sodium has sort of given it away and the chloride has snatched it up, this is our arrangement. And this is why if we have NaCl, the chloride portion is negative and the sodium portion is positive. Now I explained that in the nomenclature of inorganic compounds. So if you don't understand how I did this part, I would recommend checking out the previous video, as that's where I explain it. Okay, the next one is a covalent bond. So remembering a covalent bond is a bond that is made by sharing electrons between 2 elements. So this is where we see the term diatomic molecules. So di meaning 2, and atomic meaning atom. So if we look at chloride, so we saw chloride before and it was able to achieve 8 electrons in its outermost ring because sodium didn't want it. So chloride just took it off its hands. So what's going on here is if we draw the Lewis structure, so if we go chloride, so remembering that it has 7 valence electrons in its outermost shell, and we draw another chloride that has the exact same structure, which I'm just going to represent with X's. So what happens here is that a bond will occur because this electron will want to go here, and then this electron will want to go here. And then it'll want to go back around to here, this will want to go over to here, and you can see how, by doing that over and over, we see that bond. So that will turn into that. And this here is our covalent bond. Now again, another example is H2O. Now, as we look at water, so we have our oxygen, and we've got our 2 hydrogens. This is where they want to share. They will form this relationship where they'll just pass those 2 electrons backwards and forwards, which will look like that, which is H2O. Now, a good thing I want to sort of point out here is, I'm sure you guys have noticed already that when we draw chemical structures and we draw a bond between 2 objects, we will just draw it as a line. So how I've done oxygen, line, hydrogen, line, hydrogen. This line represents 2 electrons. That line is the same thing as me drawing Let me draw this again. It's the same as me drawing 1, 2, and just showing that they are constantly replacing each other's place.